For coming. We are so lucky to have Vinton G. Cerf, the Vice President and Chief Internet Evangelist for Google Corporation. And for those of you who have heard of Google, Vint is, his biography would take pretty much our entire hour to go.
But they can Google it, so you don't have to repeat it.
I don't have to repeat it. I do want to point out a couple of things. He is without a doubt the most celebrated and honored guest we've been pleased to welcome here at Appian. A few little highlights, like President Obama named him to the National Science Board. He's a winner of the National Medal of Freedom, along with the Tunisian Medal of something.
Medal of Science.
Medal of Science, right? Yes, and 21 honorary degrees.
It's actually 25 now. I picked 25. Up 2 more while I was in Scotland and England just a few weeks ago.
and of course, aside from pioneering efforts in all manners of different areas of science and being a visiting scholar at scientist at Jet Propulsion Laboratory since 1998, and chairman of the board of ICANN from 2000 to 2007, and held executive positions at large companies like MCI, for those of you old enough to remember when we had
before
telephones.
Before I got acquired by WorldCom and then went into bankruptcy thanks to Bernie Ebbers.
As well as positions at places like DARPA, and doing this little project I think you all know of as the Internet. Vint was the co-designer of the TCP/IP protocols and the very architecture of the Internet itself. And of course, best known as the father of the Internet.
Well, one of them anyway.
One of them, yes. But
you did pretty well, actually. Did you memorize all that?
You know, we've been working together for at least 3 minutes. So. But we are so glad to have him here, and you know, Vint's job is, of course, to contribute to policy and to spread the Internet around the Earth and also beyond throughout the solar system. So. I know he's doing a lot of projects that he may want to talk to us about today, as well as a lot of things he's done in the past. So I want to turn it over to Vint and welcome your questions later. So
thank you very much. I appreciate that. Before you say thank you, you should wait and see whether this turns out to be any good or not. And then you can say thank you if you think it was okay. Well, at the very least, you got an excuse to not do something for another 45 minutes or so. My office is literally 5 minutes away when I'm here in town, which is not too often. My staff has surf sightings every once in a while when I parachute in. I have another office in downtown Washington, which is where I'll be tomorrow. So I didn't know very much about Appian, so I Googled you and discovered that you're doing some stuff that's pretty important for the infrastructure around the U.S. and elsewhere. What is particularly important, I think, is security, and I noticed that because I had to hand in my driver's license before I could get my visitor's badge. And so I was impressed by that. I asked, why is it that you were so careful about security? And the answer was that you serve banks, and banks are very concerned about people getting unauthorized access to their information, as all of us would be concerned about. In fact, the U.S. government hasn't done very well. Some of you have been reading about the Office of Personnel Management problem. That the hosts for that, by the way, were actually run by the Department of the Interior, which now may need to be relabeled the Department of the Inferior, because they didn't do a very good job of protecting a lot of information. So let me start out by saying that what you're doing is very important, because the evolution of infrastructure that allows the Internet to be used for highly sensitive and important applications rests very much in many of your hands. Making those protocols work well and defending against the bad guys is really critical. Not only that, but we also have to defend against users who don't understand security very well, don't really appreciate secure practices. Some people still use password as their passwords because they think it's easy to remember. The trouble is everybody else knows that too. So two-factor authentication turns out to be important. So I have a question right off the bat. Does the Appian system support two-factor authentication? I'm seeing nods. Good. That's plus 5 points so far. You're doing well. Let me go back in time just for a moment or two and give you a sense for how all this stuff evolved. Way back in the early 1960s, a guy named Paul Barron was working for the RAND Corporation, and he was trying to figure out how to design and build a command and control system that could survive a nuclear attack. This was back in the days when we were all very worried that the Russians would launch a preemptive attack and that our command and control system would be wiped out. So he designed on paper an interesting network. He didn't call it packet switched, but it was. He had something called message blocks. And his idea was to digitize voice. And remember, this is 1962. This is when transistors were not all that old yet. And he had the idea that he could digitize voice, packetize it, and then stick radio transmitters on the tops of telephone poles and have them radiate in all directions. His routing system was called hot potato routing. Just get rid of whatever packet showed up in any direction that you can, and theoretically, eventually, the packets would show up at their destination. Now, Paul was not able to build that network because the conventional wisdom of the time, as expressed by AT&T and others with its circuit switching, was the only way you could do communication, and the idea of packetized voice was just silly. So he didn't get to build it, but there were other people who encountered similar ideas, maybe not even necessarily knowing about Paul's work. There was a man named Leonard Kleinbach, who's now at UCLA and has been for quite a long time. He was at MIT at the time, and he was analyzing the mathematics of queuing theory. And what he was analyzing was networks of queues, and what's being queued up were packets. So he was looking, his dissertation was called message switching, but in effect, the mathematics that he developed for analyzing networks of queues was applicable to packet switching. So this was a very powerful contribution. In fact, he got the National Medal of Science later on for that mathematical contribution to analysis of distributed networks. Another guy in England, his name is Donald Davies, was the superintendent of the computer science department of the National Physical Laboratory, and in the late 60s or so, he began looking at the possibilities of packet switching as well. In fact, he's the one that adopted the term packet to refer to this stuff, and he in fact consulted with a linguist to figure out what word would make sense. So he invented the term packet switching and built a single node network, sort of the first local area net, because he couldn't get enough money from the UK government to build more than one node of the system. So we had these three contributions in the mid-1960s. The Defense Advanced Research Projects Agency, which was created in 1958 by President Eisenhower in the aftermath of the Soviet launch of its first satellite, Sputnik, October 4, 1957. You can imagine the reaction, right? Something is in orbit. If you can put a satellite in orbit, you could put a bomb in orbit. And so immediately everybody was very concerned that the Russians would build nuclear weapons in space. So the reaction was, get us into space, and the Advanced Research Projects Agency was created to do that. NASA was a spin-off from ARPA. In the intervening years, ARPA got very interested in high-tech, high-risk, and high-payoff research in a wide range of areas, including computer science. So in the mid to late 1960s, ARPA was funding research in computer science and artificial intelligence at about a dozen universities around the United States. And every year, each computer science department would say, you have to buy us another world-class computer so we can do world-class research. And even ARPA in the Defense Department couldn't afford to do that for 12 different universities, because back then computers cost millions of dollars, had to be put into multiple rooms that were air-conditioned, et cetera, et cetera. So they said, we're going to build a network and you're going to share. And everybody hated that idea. They said, we're going to build the network anyway. So they decided to call it ARPANET, no big surprise there. And a man named Larry Roberts was seconded to ARPA from Lincoln Laboratory. He had done some experiments with point-to-point packet switching between a computer at MIT and a computer at System Development Corporation in Santa Monica. It was just a single link 2400 bit per second connection, but they showed that they could exchange packets successfully and the computers could correctly interpret the data that they were receiving. So Larry was made responsible for the management of the development of the ARPANET, this predecessor to the internet. One of my colleagues, Robert Kahn, was working at a company called Bolt, Beranek & Newman in Cambridge, Massachusetts at the time, and became one of the principal architects of what was called the ARPANET IMP for Interface Message Processor. And what was particularly amusing is that when the contract was awarded to Bolt, Beranek & Newman, Senator Kennedy sent a note, Robert Kennedy, sent a note to Bolt, Beranek, and Newman congratulating them on their ecumenical effort because he misunderstood that this was an interfaith message processing system. So I'm sure somebody kept that and put it up on the wall somewhere. So the IMP was based on a Honeywell DDP 516 machine. It was developed in about six to 9 months. And it was delivered to UCLA, where I was, the first one was delivered to UCLA, where I was a graduate student. And we had acquired a computer from a company called Scientific Data Systems called a Sigma 7. We had number 4 off the production lines, the usual bugs. That was our first node on the network, first host on the network. So I was responsible for writing the software to connect that node up to the ARPANET IMP at UCLA. Of course, it had nothing to talk to except itself. But a month later, we got another IMP installed at SRI International, where Doug Engelbart, the man who invented the mouse and invented the online system, invented hyperlinking, and a variety of other things, was responsible for hosting the second node on the ARPANET. So, by the way, I'm not going to go through all 49 or 50 nodes one at a time, so don't panic. I just want you to get some sense for how primitive this stuff was and how few in number the pieces were. So the first test of two computers talking to each other through this 2-node ARPANET was October 29, 1969. And the first attempt to communicate didn't work. There was you were supposed to type login. Now this was an echoplex system, right? So every time you typed something, it would echo back. And so he typed L, and he got an L back, and he typed O, and he got an O back. And then the system had command completion on the other end, and so it blasted GIN back, and the receiving node at UCLA wasn't ready for that, and it broke. Well, so we fixed that, and eventually got 4 nodes up and running. UC Santa Barbara and University of Utah were the next 2. So this 4-node network. By this time, it's now early 1970. And we proceeded to expand the network. A man named Steve Crocker, who is now the chairman of the board of ICANN, was another graduate student at UCLA at the same time. And upon his shoulders rested the responsibility for further development of host-to-host protocols, file transfer protocol, and eventually email, which was developed a couple of years later. So Steve created this network working group and drew on resources at the dozen universities who were part of the ARPANET experiment. And as a graduate student, he took pretty heavy responsibility for creating an atmosphere of sharing and of collaboration. And that, by the way, led to the Internet Engineering Task Force, the Internet Architecture Board, which I helped to create. And that attitude has continued to this day. This sense that you check your guns at the desk when you walk in, you represent yourself as an engineer, not particularly the company you work for, and you work for the good of what is now the Internet and what was then the ARPANET. So here we are, it's about 1970. We got a little bit working. We have file transfer and remote telnet interaction, so you could go access people's time-sharing machines. By the way, none of this would have made much sense if it hadn't been for time-sharing that got invented around 61 or so by the guys who also invented artificial intelligence, John McCarthy and who's the other guy in MIT? This is embarrassing. You mean you don't remember? God, I hate it when that happens. No, I'll think of it later. So anyway, time sharing was important because otherwise why would you have multiple people on a network trying to get access to the same machine? So as things evolved, around 71, a guy named Ray Tomlinson figured out that he could take email, which had been confined to one time sharing machine where people would exchange traffic with each other on that machine. He figured out a way to use the ARPANET to transmit a message to another machine. Sounds like, big deal, right? Except that he had to figure out, how do I identify the machine it's going to, and how do I distinguish that from the mailbox it's supposed to go into? It's basically a file folder. And he was looking around at the keyboard to try to figure out what symbol to use to separate those two, and the only symbol he could find that wasn't already in use by some operating system somewhere was the @ sign, which seemed pretty reasonable, right? Because user @ host seemed like a natural kind of formulation. That's where the @ sign came from. So this is like 71 or so. Instantly, we recognize that this is a powerful tool. First thing that happens is a few weeks later, the first mailing lists pop up. Now look, this is a bunch of geeks, right? So the first mailing list was sci-fi lovers. And, we were all, comparing notes on which authors we liked and what we thought of their books. Then the second one that popped up from Stanford was called Yum Yum. It was a restaurant review in Palo Alto, and of course that spread for a while too. So we could tell, even back in the early 70s, that there was a big social component to the network. We also made one prediction which turned out to be wrong. We thought, now that we had email, that it would be possible to reduce the cost of travel, because instead of traveling, you just interact with each other remotely. It overcame time zone problems, because instead of having to be both awake at the same time on a conference call, you could send email at any time, and somebody could respond at their leisure. So we predicted that the travel budgets would come down as a result of that. 4 years later, we tested this, and the travel budgets had gone up by a factor of 4. So, we said, what happened? And the answer was that indeed, email turned out to allow us to coordinate a large number of people interacting over a much larger geographic scope. So when you did have to get together, there were more people traveling a longer distance, and so the result was an increase in the travel budget, not a decrease. Well, here we are. It's 1972, and Larry Roberts decides that he wants to show off the ARPANET to the public. And so we install an ARPANET TIP, terminal IMP, in the Washington Hilton Hotel in downtown Washington. And we bring in blazingly fast 56 kilobit per second circuits. Actually, it was only 50 kilobits per second. That was broadband back in the 1970s. And it took 12 analog telephone lines bonded together in order to make that work with a Bell 303 modem. So we installed the TIP in the Washington Hilton Hotel. A whole bunch of us put demonstrations together, including Bob Metcalfe, the guy that invented the Ethernet at Xerox PARC. So Bob was responsible for demonstrating some of the applications on the net to a bunch of guys from AT&T. And so the AT&T guys come, they're all dressed up in their suits like this, and they're anticipating that it's not going to work, right? I mean, packet switching, it can't possibly work. So part of the way through Bob's demonstration, the IMP fails. And the AT&T guys are smiling, and they're really happy, and they left, thinking, okay, so much for that theory. Packet switching is worthless. Guess what? Some years later, not so clear. So by this time, the public, sort of, the geek public has now seen packet switching. And we started something called the International Network Working Group that included people from Europe and Japan, as well as the US, to study extensions to and evolution of packet switch networking. And that's more or less where the Internet project got started. Bob Kahn showed up in my laboratory at Stanford, because he had gone to ARPA at the end of '72, and I went up to Stanford from UCLA at the end of '72. So Bob came out and he said, we have a problem. And I said, what do you mean we have a problem? Well, he said, look, where do you think we're going to use packet switching for command and control to link we want to use computers in command and control. We want to use packet switching to link them together. But if you're really serious about this, all we have right now is the ARPANET with fixed installations. The computers didn't get up and move around. You couldn't put them on, on mobile vehicles. You couldn't put them in airplanes. You might have been able to put it in a ship at sea, although God help you if there was a spinning disk involved and the ship made a turn. So he said, I am developing a mobile packet radio system and a packet satellite system for ship-to-ship and ship-to-shore, long-distance communication, and for mobile communication, packet radio. So he said, now we have a problem. He said, well, what's the problem? He said, well, these networks don't work exactly the same way. The packets are variable length, different lengths, so their data rates are different. The satellite thing was going at 64 kilobits, eventually 128. I know that sounds so prosaic, but that was fast back then. The packet radios operated at 100 or 400 kilobits a second in mobile operation, and ARPANET was still running at 50 kilobits. So he said, we have a problem because these networks are not compatible with each other. How are we going to connect them together and make it look uniform so that any host on any of the networks would appear to be operating on a common network? That was the internet problem. And over the course of about 6 months in '73, we solved the problem, wrote a paper, briefed it to the International Network Working Group in September of '73 in England, and then published a paper in May of 1974 in the IEEE Transactions on Communications. Now, just a little side hint for you, if you're publishing anything in any of the journals, hang on to it, because that particular issue of IEEE Transactions on Communications sold at auction for $38,000. So I immediately went to my filing cabinet to see if I had any more, and unfortunately I didn't. So much for my retirement plan. So this 1974 release essentially told anybody in the world who was interested how to design and build internet. And Bob and I thought about this. We thought, well, should we patent this? Or, should we control it? I mean, look, it's in the middle of the Cold War. Why would we hand all the information about this Defense Department project to anybody in the world who's after it, including the bad guys? And then we thought some more about this, and we said, well, let's see. This thing, if it works, we, of course, couldn't know for sure, but if it works, we hope it'll survive for quite a long period of time. The Defense Department will be using it. Who are our friends? And we could make a list of friends, and who are our enemies? We could make a list of enemies in the middle of the Cold War. But they said, what about 25 years from now? Well, if you look back 25 years, you can see that friends had become enemies and enemies had become friends. So we said, we couldn't tell who would be a good guy or a bad guy. So we said, okay, let's just release it everywhere, because we want to make sure our allies, whoever they are, have access to this technology. Moreover, we knew that there were competing proprietary protocols from IBM, from Digital Equipment Corporation, from HP, and others. You could link together computers of the same brand on networks. You just couldn't get different brands to talk to each other over those nets, except in some very special cases where you build a funny little box that could talk both protocols and translate back and forth. So we said, we don't want the proprietary companies to have any excuse not to adopt the internet protocols. So we said, let's release it free of charge, no constraints whatsoever. Anybody who can build something that works this way and find somebody to connect to should be able to help grow the internet. And so this was an organic view of internet's evolution. And it worked. That's exactly what happened. People started building pieces of internet, mostly starting in the academic community. And then as time proceeded, the internet became a commercial entity, and lots of private sector companies invested in it as well. Now, you might know that when we started the work in '73, that we weren't able to actually turn the internet on until 10 years later in 1983. And the reason for that is that we had to go and get implementations done for a whole bunch of different operating systems, because back in those days, every computer maker had one or more operating systems running on their machines, and we didn't want any excuses for not switching over to the internet protocols. So we declared on January 1, 1983 that everyone would have to switch over to TCP/IP on the networks that were supported by the Defense Department. And there was, so we announced that we were planning to do that on January of '82. And we watched people implementing TCP/IP instead of the old NCP protocols. And then around June or July or so, it sort of flattened out. And so I called the guys who were running the ARPANET at the time, and I said, I want you to shut off the ability to run the old protocols. Only allow TCP for one day. And of course, as soon as we did that, I get telephone calls, you're crazy, idiot, I can't get my email, dumbass, program manager in the Defense Department. But I said, I just wanted you to know I can do that. Okay, so we started seeing, so we see some more implementation going up, and then around October, it stopped. The plateaus again, and I called up the guys running the ARPANET. I said, shut it off for 2 days. Yeah, right, but we got only 2 organizations failed to get their machines up and running on January 1st. Now, to give you a sense of scale, there were only 400 computers on the internet on January 1, 1983. Today, there are billions of devices that are internet capable. So what's happened in the meantime, of course, is that we got permission to put commercial traffic on the internet backbone around 1988. Up until that time, it was not allowed to be used for anything except academic work and Defense Department research. And also NASA and the Department of Energy had built their equivalent of internet to connect up with the rest of it, and the National Science Foundation, which funded the NSFNet. Now, this is about the right time to get rid of the Al Gore problem, so let me take care of that. When Al ran for president in 2000, somebody misquoted him as having claimed that he invented the internet, which is not what he said. He was responding to a question about what he had done as senator with regard to networking. And he said that he took the initiative in creating the internet. Now let me explain. This is the year 2000. He's reflecting back on things that happened while he was in the Senate in 1986. And in 1986, he called a hearing about research, networking, and supercomputers. And at the end of the hearing, it's like September of '86, he asked the people who were on the panel, do you think it would be a good idea to connect the supercomputers that NSF is funding together with an optical fiber network? This is 1986, and he's asking about optical fiber networks and supercomputers. The result of that question was that we all ran off to San Diego in February of '87 because it was warmer there than it was here, and came back with the National Research and Education Network program, which Al Gore, as senator, helped to fund. A few years later, he and Clinton, of course, were elected president and vice president, and he helped to facilitate legislation that allowed commercial use of the internet backbone. I'd gotten permission to do an experiment in 1988 to connect up MCI Mail, which was a commercial email service that I had developed for MCI in 1983. I got permission to hook that up to the internet. And of course, I said it was an experiment to see whether or not we could get the internet mail system to interact with the commercial mail system. The real reason I wanted to do it was to break the barrier that said you couldn't have commercial traffic on the backbone. And my rationale for that was to help the commercial sector see that there was a business to be had in commercial networking without having to go build a backbone themselves. And so indeed that worked, because by 1989, we had 3 commercial internet services in the United States. 2 of them were headquartered here. One was PSINet, which has gone away. One is UUNet, which was acquired by Metropolitan Fiber Systems, which was acquired by WorldCom, which was then acquired by Verizon. So the old UUNet system is actually in the hands of Verizon as their business network. And then there was SurfNet out in San Diego. And I didn't have anything to do with designing or building it or anything. They were originally going to call themselves SURFNet, because what else would you do in San Diego? So they had a whole campaign with T-shirts and surfing the net and all this other stuff. And then just as they're about to launch, somebody discovers that there's a place in the Netherlands, a research organization called SURFNet. And they've been instrumental in getting the Europeans up and running on the internet. So they said, well, we can't call ourselves SURFNet. Somebody said, why don't we rename our organization the California Educational Research Foundation Network, CERFNet. It sounds the same, right? Then somebody said, well, maybe we should call Vint. So they called me up. They said, can we call our network SurfNet? And my first reaction was, holy moly, what if they screw it up? I'm going to be embarrassed. And then I thought, wait a minute, people name their kids after other people, and if the kids don't come out right, they don't blame the guys they named them after. They said, okay, go ahead. So I flew out to San Diego in July of '89, and we took one of those plastic bottles full of glitter that you use in the bar scene in the movies, smash. And we smashed this bottle over a Cisco router and launched our network. So SurfNet was eventually acquired by AT&T. And I recently tried to get the network name back because they're not using it. And they said no, because they remembered when we were in competition and I was at MCI. So much for that theory. So here we are. It's 2015. We're seeing all kinds of serious issues, and we're seeing good things, too, about how the network is being applied. The serious things have to do with security. And some people say, what would you do different, if you could start over again? One answer is that if public key crypto had been available early enough, I would very much have wanted to incorporate it into the architecture. The guys that invented the concept of public key crypto are Whit Diffie and Marty Hellman at Stanford. They were 2 of my colleagues. But their first paper came out in 1977. Now, by this time, I'm here in Washington. I'm running the program for the Defense Department. It's been in development now for 4 years, since '73. And we've been through 3 iterations of the Internet Protocol design, because we would design, test, find mistakes, re-implement, redesign. So I'm on the cusp of standardizing what you're using today as 1978 rolls around, and there were no implementations of public key crypto. We just had this paper that speculated on the existence of mathematical functions that would be wonderful if you could make them work. So we didn't put that in because it wasn't available. If I could go back and wave a magic wand, I would have put public key crypto into the design. As it happens, we did make provision for cryptography, and in fact, I had started working with NSA in 1975 on the design of a secure internet. The problem is that the only technology that was available was classified. And so I couldn't tell any of my colleagues who didn't have clearances exactly how this would work. So I was schizophrenic for a long time because there were these 2 systems, one which was the one that evolved in public and the other one which was the one that was part of the military system. Today, however, we have lots of knowledge about crypto and how to use it for strong authentication, for confidentiality, and for digital signatures, integrity, and everything else. So it's time to put that stuff in place, and you're seeing it show up here and there. And domain name, the DNSSEC, for example, the Domain Name System Security Extensions, makes use of that. The RPKI, or Router Public Key Infrastructure, is another element which is sort of on its way. There are a variety of other things that we're using that for. So for purposes of looking at 2015, this is a very important component of anything you do. The problem here is that you can't secure the system at one layer in the protocol. You actually have to worry about various layers of attack. And the simple way to demonstrate that is imagine that you decide you're going to use SSL for shipping email from point A to point B, or TLS. And so you say, oh, I'm going to encrypt the messages so while they're in transit, nobody can see what's inside. That's great. What if the guy who is sending the message has stuck a virus in an attachment? It all gets encrypted. Nobody can see it. Then you decrypt it at the other end and it does its damage. So when people wave crypto around and say it's a solution to everything, it's not. But it does have a place. So that's important. The second thing is that now that the internet has got, 3 billion users on it. Oh, by the way, I have to tell you, I was talking to Eric Schmidt a few months ago. Eric is the executive chairman of Google and former CEO. He told me I can't retire. And I said, well, why not? And he said, well, you're only half done. There's only 3 billion people online. You have another 4 billion to go. So much for that idea. Anyway, we got 3 billion people online, more to come. We have probably 500,000 at least networks, not counting the personal nets that you and I run in our homes. We have probably, I don't even know how many, but 5, 6, 7, maybe billion devices that are internet capable, maybe more. They're not on the net all the time at the same time, but a lot of them are on, which is the other little problem. If I could go back, I would fix. When Bob and I were first doing this design in '73, we said, how many terminations should we plan for on the network? Now, look, we weren't even sure this was going to work, right? So it's an experiment. So we're sitting here thinking, okay, we just finished building the ARPANET, and that wasn't exactly cheap. It wasn't super expensive, but it wasn't cheap. It's a national scale net, which eventually spread to Europe. So we said, well, maybe there'll be 2 networks per country, so there'll be some competition. Okay. Then we said, how many countries are there? And we didn't know, and there wasn't any Google to ask. So we guessed at 128, because that was a power of 2, and that's what programmers think about. So we said, that's 256 networks, that's 8 bits. And then how many computers per net? And we said, well, let's go crazy. How about, 16 million? That's another 24 bits. That's 32 bits. You do the math, 4.3 billion terminations. And in 1973, that sounded like enough, to do an experiment, surely, If I could go back, I would probably pick 128, because that's what IPv6 is. But at the time, that wouldn't have passed the red face test. Can you imagine saying to somebody, I'm doing this experiment? Yes. And he said, I need some address space. Yes. And he said, I need 3.4 times 10 to the 38th addresses to do this experiment. And somebody says, that's more than the number of electrons in the universe, which, by the way, is not true. I said that once. I said, this is enough address space to allow every electron in the universe to have its own web page. And I got a note back from somebody at Caltech, dear Dr. Cerf, you jerk. There's 10 to the 88th electrons in the universe. You're off by 50 orders of magnitude, so I don't say that anymore. So those are the two things that if I could go back, I would try to change. At this stage of the game, the big issues are not so much technical. I mean, there are some serious technical issues, but the thing that is most concerning to me right now is policy. And if you've ever had anything to do with policy, you know it's much harder than engineering. At least in engineering, you can do calculations, you can do tests, you can sort of come to a quantitative decision about which idea is the better to follow. Policy is about opinion. Policy is about people who are worried about financial issues, they're worried about privacy and safety and so on, which are not quantitative. And it makes those things harder to deal with. So right now, internet governance is topic A in many places. And I spend a good deal of my time at Google on internet governance questions, policy questions around the world. Well, last thing, and then I think we need to allow you guys either to get out of here or ask some questions. The last thing I want to mention is that at this stage of the game, because we have the general public using the net, not everybody has your best interests at heart. This wasn't the case. When the internet was first being designed, we were a bunch of geeks. We just wanted to make it work. The last thing in the world in anybody's head was trying to wreck it. And so we didn't spend a lot of time thinking of how could you wreck the net. Now we have to think about that because there are people who want to do that, or they just want to penetrate the net and use it for their own nefarious purposes. Most of the guys who are doing bad things don't want to actually kill the internet because it's allowing them to generate revenue, for example, however ill-gotten that might be. But they do cause a lot of trouble, and that's going to be a big issue. Governments think they should be protecting the public from harm, which is a very reasonable thing for them to undertake. But at the same time, they don't fully appreciate that in the course of trying to protect people from harm, they may damage privacy, they may damage safety and other kinds of things. The big debate, for example, about whether end-to-end cryptography should be permitted or not is an example of a big policy issue. We went through this debate once before in the 1990s. It was called Clipper chip. The NSA said, we'll give you freely, everybody, a really high-grade cryptography. It's very strongly defended against attacks of various kinds, except for the fact that we have a back door. And the reaction to that was, no way, Jose, because if anybody got access to that back door, then all bets are off. Same argument is being offered right now that we should allow the law enforcement to have backdoor access. I think Comey, who's running FBI, is probably backing away a little bit from that. And I don't question their motivations. They're trying to protect people from bad people and from harm. But sometimes the protection may be more risky than the safety that is proposed. So I'll stop there. Oh, I'm sorry, there is one other thing. Everybody knows that we have a spacecraft that's approaching Pluto. For me, with my work at JPL, this is really exciting because I've watched this initiative from its very beginning. Some of us have been working on an interplanetary extension of the internet, which is now in operation. It's not directly supporting the Pluto mission, but it is supporting the Mars missions right now on the International Space Station. So some of us are really excited about not only the Pluto mission, but the Voyagers that have penetrated out, past the, at least the sun's envelope of the solar system. So I'm anticipating over the next several decades that we'll grow an interplanetary backbone based on standards which are not quite TCP/IP. We discovered that it doesn't work between the planets because of the round-trip time delay. 40 minutes between Earth and Mars in the worst case. Flow control doesn't work very well with a 40-minute round-trip time. And we have this other problem of planetary rotation. We don't know how to stop that. And so if you're talking to something on the surface of a planet and the planet rotates, eventually you have to wait till it comes back around again. So we developed protocols that are both delay and disruption tolerant and can deal with relays, orbiting relays. So the orbiters around Mars, which were originally sent to map the surface of the planet to figure out where the rover should go, have been repurposed as relays in an interplanetary backbone. Okay, I'll stop there. I thank you very much for your attention, and I'm happy to try to answer questions if you have them. But in any case, I hope you enjoyed this. Yes, sir?
We've got a microphone here. You talked about net neutrality, or policy.
I didn't talk about net neutrality. You want me to talk about that?
So you talk about policy.
Wine.
Net neutrality. What do you think everyday citizens or people can do about net neutrality, and your thoughts on that?
Well, Tom Wheeler has done an interesting thing with regard to net neutrality. not popular among some of the internet service providers, and that's to remap internet into Title II, which is originally designed for voice communication. So none of us thinks that Title II in its entirety makes any sense at all for internet. On the other hand, if the FCC forbears from applying most of the terms and conditions of Title II, then it can apply the kinds of requirements that one associates with common carriage. Common carriage says you have to provide service to everybody on the same terms. You can't, show favoritism. I don't think the FCC is not saying it wants to regulate prices or anything like that. It just wants net neutrality to be there so that people who supply broadband service don't take advantage of that in some anti-competitive way. Now, some of you may remember, and some of you may have read, and some of you may not know, that in the mid-1990s, during the big dot boom period, there were 8,000 internet service providers in the United States, but they were all dial-up. What was good about that is if you wanted to change providers, you just called a different phone number. And so switching was easy. When broadband technology came along, suddenly it was a truck roll to go out and install something. So you were lucky if you had broadband access from at least two providers, maybe a telco and maybe a cable company. Sometimes you had only a choice of one, and if you were in the rural part of the country, you had a choice of zero. So broadband communication was not competitive in the same sense that the dial-up was. And so we started running into the problem that the broadband provider had control over the pipe and could, if they wished, do deals that were essentially determine what you as a consumer would be able to do. We'll give favorable treatment to company A because they paid us extra, so their traffic would flow better, but company B wouldn't. If you're a startup, like you were a few years ago, and you wanted to offer service on the internet, you couldn't afford to go and negotiate with every ISP all around the world. What we want to preserve is what we'll call permissionless innovation. You want people who have an idea to be able to bring it up on the net and try it out. I guarantee you that when Larry and Sergey started Google, they were graduate students at Stanford, and they didn't have any wherewithal to go and purchase agreements or negotiate agreements with everybody all around the internet. They just brought their service up, and they were allowed to do that because they weren't required to have any negotiations about bringing up a new service. So I think that we are at a place where we have some better control over this potential abuse. It's not the right answer. The right answer should be a title in the Telecommunications Act that's specific to internet. But in the current circumstances, it's hard to see how the Congress would agree to such a thing, of any legislation at all. And of course, the other possibility is do nothing. But if we had done nothing, if FCC had done nothing, we'd still be in this awkward spot where there was potential hazard of anti-competitive behavior. So it's a good question. Thank you for asking. Next question. Yes, sir. You've got the microphone.
So I get to ask the question. You mentioned IPv6 recently.
Yes.
I mean, we've been so clever. I don't think we ran out of addresses in 1996 like we thought we were.
That's right.
Do you think IPv6 is going anywhere? Do you think we're going to continue to be clever about stretching out IPv4?
Oh, no, it's too late. We ran out officially of IPv4 address space at ICANN in 2011. So you must know that already, February. ARIN, the America's Registry for Internet Numbers, which I chair now, ran out just recently, and all the others are out. So the regional internet registries do not have fresh IPv4 address space available. If you're looking for IPv4 address space, you're going to be out there on the market trying to buy it. This is bad news in many respects. First of all, people who still have IPv4 addresses that they don't need are going to try to whack it up into little pieces and sell it for the maximum they can. Guess what? Every time you whack off a little piece, it's another line in the routing table. We just popped past 512,000 entries in the routing table. Some of the routers can't hack more than that. Pieces of the internet started falling off. So this is a bad scene. Where we want to be is running V6, where we allocate big chunks of address space so people never really run out. And I was despairing, right? So it's 96, we get the standards done. Here it is almost 20 years later. But I can tell you that we're starting to see serious IPv6 adoption. There are some places where the users are 40 or 50% using IPv6. Some people don't notice it, which is good. That's the way it should be. So at this stage of the game, I am now more optimistic than I have been over the last 2 decades about implementing IPv6 because there really isn't a whole lot of alternative. And the software is already in the edge devices and it's in the routers. It's a question of turning it on and finding the bugs in the implementations. I mean, I'm not going to hide from the fact that if you don't have a lot of experience running IPv6, there are going to be bugs. Sir?
Yes, so I know a lot of companies like Google and Facebook, large companies, both for altruistic and good business reasons, are focused on getting the world connected. What do you think that some of the bigger hurdles are, and when do you think we'll start to see bigger penetration into the areas of the world that have traditionally been underrepresented?
Yeah, it's a good question. The first observation is that economics really counts here. And that's, the fact is that it costs money to build infrastructure that will support internet. And that means that the people who are in less well-off economic circumstances have more trouble getting access because of the cost. Fortunately, I think physics is our friend here, and the costs are coming down for the equipment. Certainly, the smartphone has made a huge difference. Lots of people are experiencing internet for the first time with a smartphone. And for many of them, that may be the only way that they experience the internet, which is why Google and others are spending a lot of time focusing on, mobile first. So that's one thing. The second thing is that there are a variety of alternative technologies now for allowing people to get access to the internet. We're investing in a lot of them. We invested in a company called O3b, which stood for Other 3 Billion. It's a satellite system that's now in orbit around the equator. It's at 8,000 kilometers orbit. The good news there is it's 50 milliseconds up and down instead of 250 at synchronous. And second, they can see 40 degrees north and south of the equator. And third, each satellite can deliver 10 gigabits per second of data over 10 different spot beams. So it's a gigabit per spot beam, and they can aim them at different places. So it covers a lot of the Pacific Islands, it covers sub-Saharan Africa, it covers South America, and so on. So that's been a good investment. The second thing that we did, is you all know about the Loon project, which is called that because it's so loony. We've now got to the point where we have balloons that can survive multiple circuits around the Earth at 60,000 feet. And they control their latitude by moving up and down in the jet stream, which is not always going in exactly the same direction. So that's turned out to be feasible. And so now we're looking at the possibility of commercial operation. The third thing that we did, and others have done, we bought a drone company called Titan Aerospace. And they were thinking about using drones for the same purpose, to deliver internet access. Some of you know that we've been building gigabit fiber services in the United States, starting in Kansas City. I've been trying to say, what about, Reston? What about McLean? How about Loudoun County? Well, I know the guys who are doing the work, and so I'll keep pestering them until maybe we'll all get a chance. So that's been moving very well. And what's interesting is to watch what happens when people have gigabit speed service on an end-to-end basis. One thing that's interesting is that it only takes about 15 seconds to download an hour's worth of video. And so it changes your understanding of what video on demand means, because in this case, you're downloading faster than you could watch it. So you just download the thing and play it back whenever you want to. There are some intellectual property issues associated with that, because now you have a copy of the thing, and some people worry about that. So that's another thing that we've been doing. And finally, we've been looking at Wi-Fi and extensions of the net. In New York, for example, there are these telephone booths that nobody's using anymore, but it has power, so you can just plug a Wi-Fi service in there and radiate. In India, there's this Digital India program. Prime Minister Modi wants to connect 250,000 villages with an optical fiber network. If you talk about India and China, add 3 zeros to any number you're thinking of, in order to get a sense of magnitude. Then he wants to extend that fiber network, either with fiber or Wi-Fi or something, to connect another 350,000 villages. That's 600,000 villages in India. So there's real energy going into internet expansion, creating business models and incentives for people to build that infrastructure. The World Bank is focused on funding that sort of initiative now, which it wasn't in the past. So I'm of the belief right now that we're driving enough cost out that people who are in lower income levels will be able to afford it. The Chromebox that we make, Chromebook, is getting down into the $270, $280 range. which is not too far away from where Nick Negroponte was trying to get the $100 laptop, one laptop per child capability, which was several years ago. So prices are coming down. You have a microphone.
I do.
We will allow the microphone to drift back that way too, in case people are thinking we're favoring everyone up front. Go ahead.
It's been a whole hour since I've talked, so clearly something has to happen. So you mentioned James Comey, and he and David Cameron both have been making a push against end-to-end encryption, against the so-called going dark problem. There have been a couple of reasons posited for why that's happening, whether it's an attempt to sort of bully Apple and Google and others into dropping encryption, or whether it's really an attempt to try and legislate some backdoor model. What do you think the cause of that is, and what can be sort of done about it? It feels like some of it is a lack of willingness or a lack of technical understanding of the realistic. Yeah.
These are political statements in part, and let's be fair about this. I did mention in passing that most countries believe their purpose is to provide a safe society for citizens, which means that if you remember Rousseau and the Social Contract, in very rough terms, it said you gave up a certain amount of your freedom of action in exchange for safety in the society. If we had a society where there were no constraints whatsoever, and I go up and shoot you and I have no consequences at all, this is not good for you. On the other hand, if we had a society where everybody, there is no privacy at all, everything is transparent, everybody knows what you're doing and what you're planning to do and everything else, that's probably not a society you want to live in either. So there must be some place in between where we will tolerate giving up a certain amount of our freedom and maybe giving up a certain amount of what we consider privacy in exchange for this safer environment. So most countries, not all of them, but most countries, I think, see this as an obligation, most democratic countries anyway. The question, though, is how to realize that obligation as an administration. And that's where you get tension. Some of it is purely political, as in, I will tell the people that I'm going to protect them from harm. Look at all the bad things that happen on the net. You read about it every single day. I'm trying to protect you, and the way I'm going to do that is to ban cryptography, which allows the bad guys to do things that we can't see. Of course, what that means is that you can't protect yourself and your own privacy. And I don't think this is entirely a consequence of not understanding the technology. I think this is a kind of political play. If I'm trying to get reelected, I want people to elect me because they think I'm going to do something for them that others won't. And one of them is to say I'm going to sprinkle safety pixie dust all over everybody. So I don't think that Comey is that way. I don't think this is a political play. He's not an elected politician at all, but he's responsible for trying to protect citizens from harm. And he's trying to figure out how to do that in the face of this new technology. Well, we've had new technologies come along. Imagine when the bow and arrow gets invented and somebody says, holy moly, that means you can hurt somebody remotely. Maybe we should ban that because, you can't protect yourself from these things. Well, that didn't happen either. At some point, we do have to ask ourselves, what can we do to help law enforcement protect us, and how much are willing to tolerate in terms of our either loss of privacy or loss of freedom of action in exchange for safety and security? And each of us is going to have to try to answer that question. Different cultures will have different views of that. Different countries will have different views too. I don't think it's a one answer. I still am over here on the side saying I don't think we should breach, we should not create a legal requirement to breach privacy that's achieved by cryptography. I still think that we need that capability to protect ourselves from potential harm. But that's going to be a debate for a while. Okay, who else has a question? This is your job is to run around. This is part of the health plan here at Appian, is to run around with the microphone.
Thank you, Fitbit.
And somebody else has to keep track of time because I don't want to keep you away from work for too long. Haha. I'm going to walk down here in case I have to lip read. In case you don't know, I'm hearing impaired, so I don't want to be the guy that came to talk and didn't listen. Yes, sir.
With so many widely publicized security vulnerabilities in the past 18 months, Heartbleed, Shell Shock,
there's been a lot more attention on open source projects like OpenSSL. What do you think the future holds for projects like that are so widely deployed across the global infrastructure that have such a low amount of resources dedicated to them?
Yeah. So to be honest with you, the openness is a good thing, right? Because we can all see how it works and what it does. I think companies like Google and others have an obligation to try to help support that. So we push pretty hard on open stuff. I mean, our Chrome browser, for example, and our Android operating system is open source. So I'm a big fan of that. The big problem with these kinds of projects is making sure that the software actually gets properly curated, gets updated. And by the way, even when you come up with, suppose you find a bug, like the OpenSSL, how do you, even if you find the solution to the problem and you revise the code, how do you make sure the code actually gets installed in all the places where it needs to go? That's still something of a conundrum. Getting software to be updated when it needs to be is really important. And there are a few ways that have been implemented to do that. Microsoft has this automatic update. Apple does automatic. We do automatic updates at Google. We drive our own updates. We don't rely on somebody else to do that. We may be taking somebody else's code, but we'll look at it first to the extent that we're able to before we allow it to be updated into our own systems. But I think you're putting your finger on a very important point, which is how to sustain an open source environment. Let me give you one other example of why open source turns out to be so valuable. I'm going to go up here so I don't have to turn my back on everybody. Some of you may have been around in the, well, let me take 91 as a key year. This is when Tim Berners-Lee releases the World Wide Web, and nobody noticed. He had it running on a Next machine, which was, Steve Jobs' company after Apple. So that was an impressive accomplishment, but honestly, not too many people noticed. The next thing that happens, though, a couple of years later, Mark Andreessen and Eric Bina, the National Center for Supercomputer Applications, released the Mosaic browser. Now, this turns the internet into a magazine. You're seeing images and nicely formatted pages and everything else. Of course, everybody gets excited about that. The reason I bring this up is that all of the browsers of the time, and even up to today, have the property that you can see what the HTML was that produced the page. You can say view source or show source. That's the ultimate in open source training. And in fact, the term webmaster was just invented, right? There was no, you couldn't go to school to become a webmaster way back then. The way the webmasters learned was to learn from each other by looking at their source code. And it was a dramatic evolution for people who could take somebody's source code and fiddle with it, change it, add some features, and then show that off. And everybody learned from that. So learning was really powerful, and open source has the property that allows lots of people to learn from everyone else. I really like that very much, and I think it's an important part of the computer science world, and it should be. The problem is that even when you have open source, you have to be sure that if you're downloading, let's say, an executable, or maybe downloading object code, how do you know that it came from the open source that you were looking at? And in fact, how do you know where it came from in the first place? Even if it's open source, not everybody is in a position to actually read the source code and decide whether it's okay or not. So we now need very strong authentication and some means of assuring that the updates that we get are coming from the place that they should be and not someplace else, which is one of the reasons that the domain name system and certificate authorities have become troublesome, because some certificate authorities have been compromised either by direct attack or by bribery or some other, somebody nefariously deciding I'm going to create certificates that say Google or Microsoft or something else and allow people to mistakenly download and install software that has bugs or has deliberate, not bugs, but has deliberate malware. So there's an ecosystem that is still not quite right for making sure that open source does the job that we all would like it to do. It's not just a question of supporting the people who are writing the source code. The Red Hat guys have found not too bad a model for dealing with Linux. They're basically saying, let us curate the code. We will take care of making sure you get updates and everything else. And that's turned into what I guess is a reasonable business. So looking for business models that will support that's pretty important. It doesn't have to be for profit. could be a not-for-profit thing, could be a subscription thing, it could be premium or freemium kinds of models. But we need those in order to sustain that development. Okay. I leave it to you to decide. One more? Okay. Everybody wants to get out of here, basically. I think. One question. Okay, one more.
So, being in the position that you're in, you probably get a lot of attention, and if you do make a mistake, is it difficult for you
to recover from that?
Yeah.
Of course, the cheap answer would be, well, I never make mistakes. Let me tell you, this is a kind of a life lesson coming from some old fart. When I was at UCLA working on the ARPANET, I had a dissertation that had nothing to do with networking. It was about multiprocessors and models of trying to figure out how to take serial code and turn it into parallel code without having it, collide with itself. So I was asked to. What's relevant is I was an undergraduate at Stanford in mathematics. Okay, so I go to UCLA, do my MS and PhD in computer science. The guys at Stanford said, "Why don't you come up and tell us about your dissertation?" Which I did. A little while later, I got a call saying, "We want you to join the faculty," and I said no. And the reason I said no was that I'd been there as an undergraduate. I knew how smart those kids were, and I said, I don't have anything to teach them. They already know more than I do. And I said no, and they said, we won't take no for an answer. And I had people like Don Knuth calling me and saying, you have to come up. And at some point, these are the people that wrote all the textbooks that I remember learning from. And at some point, you can't say no anymore. I'm a little puddle on the floor. So I went up to Stanford. That's the first time I tried to say no, and it didn't work. A little while later, I'm at Stanford, we're doing the internet stuff. Around 1975 or so, the ARPA guys say, why don't you come back here to Washington and run the internet program for us? And my first reaction was, geez, if I screw up, everybody's going to know. All my friends are going to see me fail. So I said no. Well, that didn't work either. I started getting beaten upon by people that I had high respect for at ARPA. So I said yes, and of course I don't regret it. The object lesson here is that when you're young, you can afford to say yes, even if you screw up, because you can recover from that. So the honest answer is I've been very lucky. I have people who have kept me from doing terribly stupid things, but this is a management lesson. If you get to a certain level in management, you have to make sure that the people who report to you feel free to tell you you're about to do something dumb. And the problem is not that they're afraid to say that. They make the assumption that you've already figured it out, and if you told them to do X, it means you already figured out that it was okay to do X, and that all the bad stuff you have discounted. Except that's not true. You may not know that doing X is going to be really stupid. And I have to repeatedly remind people that report to me that if I tell you to do something and it's stupid, you need to stop me and tell me it's stupid. Well, you need to tell me why too, so I can learn. But this feedback loop is really important. So I've been very lucky. I haven't done too many stupid things. People have prevented me from doing anything really bad. And on the whole, you just survive that. Criticism is okay. All right, that's all the time we got. So I'll turn this back over to you, and I'll thank you all for your time.
Thank you. Round of applause for Vince. Thank you.
Thank you.
All right, thank you, everyone. There are still a lot of donuts left for those of you keeping track, and please, thanks again to our fabulous guest for that fantastic
you're
talk.
welcome. And we're right on time. It's perfect. Thank you.
That's it for this morning. Thanks again for coming and visiting us at Appian, and for those of you from the College Board, thanks for joining us. And we'll let you get back to work. Thanks.
Oh, I didn't realize that we had College Board folks here too. I thought you were all Appian. Well, thanks to the College Board for making more graduates happen. Thanks very much. I appreciate it.